Hello, everybody, both on Zoom and on YouTube. It's a pleasure for us to have Dr. Carlos Hernandez Garcia today speaking in the Atto Fridays. He is an associate professor at University of Salamanca, Spain. He did his PhD in 2013, and after an European Marie Curie postdoc stay at GILA, University of Colorado at Boulder, he returned to Salamanca, where now he leads the unit of structured light and matter, LUMES, and the ERC starting grant project Atto Structura. So we're going to have a talk about structured light, which is very important in our field. And his work focuses on the generation and applications of ultrafast structured light pulses at the intersection between the fields of structured light and attosecond science. Together with his colleagues and collaborators, he has designed theoretical tools to understand and combine quantum simulations with highly nonlinear strong field processes. And he has received several prizes, such as the Fresnel Prize in 2019, the UPAP Young Scientist Prize in 2021, and the ECO Prize in 2023, ICO, ECO. I never know these acronyms. Anyway, but lots of prizes, congratulations, and we're looking forward to your talk. So the floor is yours. Welcome to the Atto Fridays, you and everyone else watching.
Okay, thank you very much, first of all, Carla, and all the organizers of Atto Fridays. I'm really humbled to be part of this seminar, and I really congratulate you also for putting together this seminar. It's really fantastic, and well, I hope you like and you enjoy this world of structured light and attosecond science. I will share my screen right now. Hope that you can see it. So today I'm going to talk about the work that we've been developing at the University of Salamanca in structuring light pulses at the attosecond timescale. So I've structured this talk, as you can see here. First, I will give a brief introduction of what we know as a structured light. And then I will show you the roadmap that we have followed during the last decade, more or less, towards generating extreme ultraviolet attosecond pulses that are also structured. And lately I will mention, and I will try to finish with one of our most recent works in generating spatiotemporal optical pulses in the extreme ultraviolet and also at the attosecond timescale. Okay, so as Carla mentioned, I come from University of Salamanca in Spain, where we are experts in developing theoretical tools for simulated harmonic generation that have allowed us to guide this new and emerging field of structured light in these ultra-fast regimes. When we talk about structured light, what do we mean by structured light? Okay, so there are nowadays a myriad of possibilities to structure light. So starting from the plane wave description that we are learned in basic optics, we can structure light in frequency, amplitude, time, space, polarization, and phase. Okay, in our field, we are very used to structure light at the time, domain, temporal domain, and spectral domain to generate ultra-short pulses. Maybe we are not that used to structure light spatially in polarization, phase, and amplitude. And actually, when we talk about the structural light, typically we are talking about spatially managing the properties of polarization, phase, and amplitude of our light beams. And I can try to more or less convince you that these properties can be very well described through the angular momentum of light. So for those of you that maybe don't remind very well what is the angular momentum of light, let me remind you that there are two kinds of angular momentum. Spin angular momentum that relates to polarization, and we can have spin 1 or -1, depending if it's left-handed or right-handed circular polarization, or we can have linear polarization, which is a proper combination of these two different states. But also we have another kind of angular momentum, which is the orbital angular momentum. And the orbital angular momentum relates to the macroscopic structure of a light beam, and actually how is the amplitude and phase distribution of a light beam as it propagates. It is characterized through the topological charge that refers to the helical phase front of these beams. So for example, if we have a Gaussian beam, we have a flat phase profile along the transverse plane, and the intensity is the standard intensity profile that we have, no angular momentum. But as soon as we start to have some phase variation along the azimuthal coordinate, as you can see over here, this phase variation is characterized through the topological charge, which is the number of 2 pi phase shifts that we have along this profile over here. And in these cases, we have a phase singularity at the center that translates into a null onto a donut profile in the intensity profile. Yeah, and the number of 2 pi phase shifts that we have along the transverse profile, it's characterized by the topological charge L equal 1 in this case, L equal 2, these 2 pi phase shifts along the transverse profile. These beams are also known as vortex beams, yeah, also characterized through their topological charge. Okay, these two different types of angular momentum, they can be combined, of course. So we can have vortex beams with different polarization states. How can we plot this? For example, let me plot these little green arrows over here. So these are linearly polarized vortex beams, those ones that you can see over here. And you can actually see the phase relationship between the different arrows according to the phase relationship that we have in these cases in these two kind of vortex beams. Okay, so generating these beams with either spin or orbital angular momentum, we know very well how to do it, and we know very well how to do it in the visible or infrared regimes. Okay, I think all of us have used at some point some waveplates to convert from linearly polarized to circularly polarized beams. And also, we can imprint orbital angular momentum through spiral phase plates, like this one you can see over here, or through spatial light modulators. And there are many techniques, very well developed, but they are very good in the infrared and visible. However, if we would like to imprint these properties into the extreme ultraviolet, where we can generate Attosecond pulses, we have a problem. And the problem is very well described by this plot that we have over here, very well known in optics, in physics, that the refractive index, as we go towards these high frequency regimes, tends to 1. So basically, these devices are transparent to light, so they are highly inefficient in this regime. So here we face a problem if we want to generate structured light beams with this control angular momentum, because these techniques are really highly inefficient. So over like 10 years ago, something like this, there was a proposal, why not using high order harmonic generation to generate extreme ultraviolet or even soft X-ray beams with controlled spin and orbital angular momentum. And here we change the paradigm a little bit, because instead of imprinting these properties, why not generating beams with these properties already? Or, in other words, in harmonic generation, up-converting the angular momentum properties from our intense driving field towards the extreme ultraviolet, to the harmonics that are generated, and why not into the Attosecond pulses. Okay, so I know that in these web seminars, most of us, we are very used to harmonic generation, when we have our driving field, typically our gas jet and generated harmonics. And now the question that we have to ask ourselves is how these properties of spin and orbital angular momentum are converted into this high frequency ultrafast regime through high order harmonic generation. Okay, so let me now enter into the second part of my talk, in which I will show you the roadmap that we have followed towards this translating Attosecond pulses into this structured light regime. Okay, so it's more or less like a decade in which we started thinking or making the first experiments in generating circularly polarized harmonics, translating spin angular momentum into the extreme ultraviolet, and high harmonic vortices, yeah, translating orbital angular momentum into the high order harmonics. Let's try to understand and to follow how this translation, this mapping can be properly done. So let's start with spin angular momentum. So typically, when we drive harmonics and the very first experiments, we have a linearly polarized driver, the high nonlinear interaction, very well explained by the three-step model. And as a consequence, linearly polarized harmonics are generated. Here you can see the single atom picture, the wave packet dynamics that follow along the polarization axis of the driving field, where we have this three-step process that is able to generate harmonics. So if we would like to generate circularly polarized harmonics or even circularly polarized Attosecond pulses, we might think, okay, maybe we can just change the driver and use a circularly polarized driver. However, here we face a huge problem. If we use a circularly polarized drivers, we have no harmonics left. And this can be very well explained through the three-step model or from the quantum picture, in which the wave packet, once it's ionized, it is driven away from the parent ion, and it does never recollide, as we can see here in this model over here. And this was already very well known experimentally since the early 90s. Okay, so how can we circumvent this limitation, this problem to generate circularly polarized harmonics? So maybe we can think ourselves, okay, if we are driving our wave packet away with a, let's say, right-handed circularly polarized field, why not using another field that is left-handed so we can drive our wave packet back to our parent ion? All right. So maybe using a combination of right-handed plus left-handed, we can have it. However, if we have right-handed and left-handed, this is a linearly polarized field. So we are still in this situation over here. However, we can think a little bit more about this scheme. So if we think that our driver is composed of a left-handed circularly polarized and a right-handed circularly polarized, still our driver is linearly polarized, and the different harmonics, or the harmonics that you can see over here, they are linearly polarized. But if you look carefully over here, we do have circularly polarized harmonics. We do have them in this plot. Can you see them? They are there. The thing is that they are hidden. They are hidden because, in fact, a linearly polarized harmonic is not more than a combination of right-handed and left-handed. So the circularly polarized states, they are already in this scheme of linearly polarized harmonic. The problem is that they are overlapping between the two different states. They are overlapping both in energy or spectrum and in space or in divergence. So what we could think, okay, we should break the symmetry of the driving field so we can experimentally separate, either in energy or in space, the two states of harmonics that are over there. And if we are able to separate them, maybe we are able to generate or to observe circularly polarized harmonics. And for that, what we need is a conserved physical quantity in the harmonic generation process that allows us to do this. So for example, as a conserved quantity, we can use energy, the photon energy. Why not imprinting different photon energy to either of these two fields that we have, the driving fields? So if, for example, we use left-handed 800 nanometers and right-handed 400 nanometers, omega and 2 omega, we have this threefold driver. And using energy, we can separate the harmonics in energy. We can generate a train of harmonics, a comb of harmonics, sorry, that is composed of pairs of harmonics, left-handed, right-handed, left-handed, right-handed. And actually, if we look at the wave packet dynamics in this case, this is the driving field that results from this superposition. The wave packet dynamics, they allows this recombination process, and they allows the generation of harmonics. So this was one of the first technique that was able to generate circularly polarized harmonics to separate the circularly polarized states in energy. And this was very first done in early theoretical works by Wilhelm Becker and Jan Milosevic and co-workers that were confirmed experimentally by the group of Oren Cohen in 2014, something like this. And since then, there have been many, many works that have demonstrated with different approaches that this scheme is really nice scheme to generate circularly polarized harmonics. Okay, so this is in the spectral domain, but what about the temporal domain? these harmonics that are generated over here, how are the Attosecond pulses emitted? So we should combine all these harmonics, perform the Fourier transform, and go to the temporal domain to see how the Attosecond pulses are emitted. And if we do this, what we see is a kind of very structure of a strange Attosecond pulse string in which each pulse is linearly polarized, but with a 120 degrees rotation from pulse to pulse, according to the threefold driving field that we have, okay? So still, as we have this combination of right circular and left circular harmonics that are overlapping in space, we are not able to generate circularly polarized harmonics unless that we suppress one of these two families of either right-handed or left-handed harmonics. So this is using this quantity of photon energy, but we can use another physical quantities to try to separate these circular and right-handed, left-handed circularly polarized harmonics. What we can use also is the linear momentum, okay? So we can have two drivers with different linear momentum, which is no more than using a non-collinear scheme, as you can see over here. So right circular, left circular, same photon energy, let's say 800 nanometers. And in this case, when they have linear momentum, what we can see is that the harmonics, right circular and left circular, they are separated in the far field domain. And you can see over here that in this case, the linear momentum translates in a spatial separation of the two different components, okay? So what we have, it's in our camera, we have two main beams with harmonics going in either of these two directions, thanks to having this non-collinear scheme of harmonic generation. And in this case, how are the Attosecond pulses emitted? So as they are separated, the two components in space, what we can do is to filter out one of these components, and as we have just one of these components, in this case, yes, we can see circularly polarized Attosecond pulses, okay? And this is one of the works in the group of Min Chan Chen, also with Henry Captain and Margaret Murnane, where they were able to observe experimentally these pulses filtering out one of these two branches over here. Okay, this is with linear momentum, but we have more physical quantities. And in this topic of structured light, we have also orbital angular momentum. What happens is we use orbital angular momentum, and in each of the two drivers, we use different orbital angular momentum. What we can have is that we have a spatial separation, but in this time, the spatial separation is in different rings. Each component has a ring of different size. So we can separate the two components, left-handed and right-handed, in space in different rings. Yeah, and this is, for example, on a scheme of an experiment that was performed in Gila in the group of Henry Captain and Margaret Murnane, with drivers with different and opposite orbital angular momentum. And thanks to this proper combination, as you can see here in the experiment and in the theoretical results, the harmonics are generated in two different rings, right-handed and left-handed. So in summary, here you can see that using these physical quantities, different physical quantities, we can go and separate the two different components of harmonics and to be able to control the spin angular momentum of the higher order harmonics. And thanks to all these schemes nowadays, we do have high harmonics and Attosecond pulses with controlled spin angular momentum. Okay, so I've talked already about orbital angular momentum, but let's go a little bit more in depth in the generation of high order harmonics with orbital angular momentum with optical vortices. So as we did for the spin angular momentum, what happens now if we drive the high order harmonic generation process with a driving beam that is a vortex beam? So for example, in this case, we have a vortex beam with L equal 1. Here is the 2 pi phase shift along the transverse profile, the donut ring intensity. And the question that we ask ourselves now is, how are the harmonics generated? What is the topological charge of the different harmonics? And what we found out in our simulations is that the topological charge of the different harmonics, it scales with this quantity that you can see over here, which means that actually it is proportional to the topological charge of the driving field through the harmonic order Q in this case. Okay, and this is a result of orbital angular momentum conservation that we actually can understand very well in the photon picture. Because, for example, if we want to generate the 17th harmonic, what we are doing in harmonic generation process is to absorb 17 photons, 17 infrared photons with L equal 1 from the driver, and emitting a single photon that through orbital angular momentum conservation, it requires to have L equal 17, okay? So it seems simple, but it was not that simple because there was a first experiment in which this observation was not very clear. But fortunately, afterwards, there have been different groups in the group of Paul Corcum in Canada, the group of Thierry Gouchon in France, that they were able to verify this conservation law. How do the harmonics look like? So these are the results from our simulations that were performing this work over here, in which this is, for example, the intensity and phase profile of two different harmonics, 17 and 23. We have the donut profile. If we look at the phase profile, we have this, if you count over here, you can count 17 phase jumps, and in this case, 23 phase jumps. There is a more clever way of characterizing the topological charge, which is actually performing the azimuthal Fourier transform over here, and this is the result that you have down here that we can characterize this very well. So one of the things that the process of harmonic generation allows in the generation of these vortices in extreme ultraviolet is that we can generate vortices with very high topological charge. Instead of, for example, if we use L equal 4 as the driving beam instead of L equal 1, and if we look into the harmonic 25, that we will go already to a topological charge of 100. And actually, this was measured in a collaboration we had with the group of Sophie Casamias, a work performed mainly by Alok Pandey and Alba de las Heras, in which they were able to observe and characterize harmonics with topological charge up to 100. Yeah. Okay. Again, this is the spectral domain, but what about the temporal domain? How are those harmonics emitted in the temporal domain? Let me, to understand this, let me just remind you the basics of harmonic generation in going from the spectral to the temporal domain. So if we have a typical spectrum of harmonic generation, this is the driving pulse, these are results from macroscopic simulations we did. So if we took just one harmonic, for example, the harmonic 33, and we perform the Fourier transform, this is what we get. We get the harmonic 33 is emitted in the femtosecond timescale similar to that of the driving pulse. Yeah. However, as soon as we include, for example, another harmonic, 23, 33, and 35, we start to have modulations in the temporal domain. And as many harmonics as we include, these modulations result in shorter and shorter pulses. If we include all the high order harmonics, we have then our very short pulses in the Attosecond timescale with some chirp that comes from the phase relationship between the different harmonics. This is the standard scheme of harmonic generation that is very well known, but the question is, okay, now if we translate this into our orbital angular momentum harmonics, how are those emitted in the temporal domain? To understand this, let me just go again, and now let's pick, for example, one of these harmonics. For example, for simplicity, let me take harmonic 21st with L equal 1, okay, just for simplicity. How is this emitted in the temporal domain? So this will be what we can call a femtosecond vortex pulse. Yeah, you can see the harmonic 21st, the electric field with the wavefronts associated to this topological charge that integrated all together is a pulse that is emitted at the femtosecond timescale. Okay, what happens now if instead of one harmonic, we have a combo of harmonics with different topological charges? Again, for simplicity, let's go from 1 to 9. In this case, harmonics 17 to 25. Okay, these are very simple simulations. Of course, in the results of harmonic generation, the topological charges are typically highest. Okay. What happens in this case? It's not easy, yeah? It's like we were talking about harmonics with spin angular momentum. We have this combination of spin angular momentum, and here we have a combination of orbital angular momentum. So how is the temporal profile? So the answer is actually this one. It's not as easy, yeah? It's what we call a light spring, which is actually two intensity helix that are intertwined, yeah, that are actually emitted in the attosecond timescale, in the sense that we call this an attosecond light spring. And this can be interpreted as if you have an attosecond pulse train that is delayed along the azimuthal profile, as you can see over here. So the attosecond pulse, if it's delayed along the azimuthal profile, this is what is an attosecond light spring. So this is what we predicted from our simulations back in 2013, and in a very nice and fantastic experiment in the group of Thierry Gouchon in 2016, through rabbit measurements, they were able to characterize actually this quite complex attosecond light spring that results for driving harmonic generation with a vortex pulse. Yeah. Still, if we integrate all this signal spatially, this signal is still emitted at the femtosecond timescale. So although we call this attosecond light spring, we cannot talk here about attosecond pulses, yeah, because this signal, if integrated, is at the femtosecond timescale. How can we obtain then attosecond pulses that have the vortex structure, or attosecond vortex pulses, let's call them like that? So that I can tell you that we would be able to obtain them if we are able to generate a comb of harmonics, all of them with the same topological charge. In such a case, for example, in this one, and if we compose those harmonics, what we do have is this structure. Yeah, it is more familiar to us in the sense that this is what we would expect from an attosecond pulse train, different attosecond vortices that are emitted along a pulse train, as we know from harmonic generation. However, as you can imagine, we have a challenge here ahead. Yeah, how can we generate all the harmonics with the same topological charge? This is a challenge because from orbital angular momentum conservation, we know that we have this scaling over here. So it is not easy, yeah? It is not straightforward to force all the harmonics to have the same orbital angular momentum. Okay, let's see how can we do this, and let me just travel a little bit through different schemes that we've developed in Salamanca that ended up in a scheme that was able to actually generate these attosecond vortex pulses. And to start with, let me just change this scheme, and instead of considering just one vortex driving field in the infrared, let me just consider a combination of two. What happens if we combine a vortex field, a driving field with L equal 1 with L equal 2? If we have this combination, this is the phase profile and the intensity profile that results from this combination. And actually, in this case, the result is quite different, because now each harmonic order exhibits or is composed of a combination of topological charges. Yeah. How can we explain this? This can be explained again if going to the photon picture. So let's try to understand again the generation of the 17th harmonic. Now we have to pick 17 photons from the driver. But as you can see, there are many options. Yeah, depending on how many photons I take from each one of the drivers, I will have different paths, and the resulting topological charge of the resulting 17th harmonic will differ depending on how many photons we choose from each one of these drivers. Okay, so this explains why now the 17th harmonic exhibits all this topological charge. Which topological charge will dominate? Which one will be higher? It depends on the weight, intensity weight between the two driving fields that we have over there. Okay. So this is, for example, how the results from our simulation, now the intensity profile of the 17th harmonic, the phase profile. Now it's more complicated, yeah, to measure directly the phase over there, but if we perform the azimuthal Fourier transform, there we can see how there are many contributions over there. For those of you that are more interested into this is a very beautiful work that we developed with our student at the time, Laura Rego, in which we were able to identify that the short and long trajectories of harmonic generation have different contributions of different orbital angular momentum values over there. And you can find this work over here if you are interested into that. Okay, so this is the first scheme we tried. But now the next step we perform is, okay, what happens now if we perform a time delay between these two driving things that we have over there? So this means that our driving pulse will be this green pulse, in which at the front part of the pulse we have, for example, L equal 1, and at the rear part of the pulse we have L equal 2. So L equal 2. So if, for example, let me just try to explain the generation of the 11th harmonic for simplicity. So at the front part of the pulse we will generate 11th harmonic with L equal 11, at the rear part of the pulse, 11th harmonic with L equal 22, 2 times 11. And in the middle, what about the middle? So in the middle, what we will have is, depending on the weight between the two pulses, we will have all the contributions from 11 to 22. And this is shown in this movie I will plot over here. Starting from here, we have L equal 11, and as soon as we move through the pulse, you can see how the orbital angular momentum is evolving from 11 to 22. So at that time, this work was quite novelty, because we were able to define a new property as the torque, or the self-torque of light, that meaning that within a pulse, we can have a pulse in which the orbital angular momentum is changing in time, as you can see over here, okay? And luckily, this was quite simple. I wouldn't say simple, but quite easy to measure experimentally, because you can think, okay, how on earth can we measure the orbital angular momentum of a light pulse that is changing at the femtosecond or even sub-femtosecond time scale around the pulse? So it was quite straightforward, because there is a direct relationship between the self-torque, or time-dependent orbital angular momentum, and the azimuthal chirp. You can work out the instantaneous frequency, and if you work out the instantaneous frequency of a laser pulse, there is a term that depends on the azimuth and depends on the variation of the topological charge on time of the self-torque. It means that if we are able to measure a light beam in which there is an azimuthal chirp, automatically there is a temporal variation of the orbital angular momentum. Yeah, and this was measured in the lab of our colleagues at Colorado, and the group of Henry Captain, Margaret Murnane, and Kevin Dornay at that time was able to measure the self-torque of this beam, and to actually confirm that this property is present naturally in harmonic generation if driven by a driving pulse of 2 OAN properly time delayed. And actually nowadays, this work has inspired other configurations using metasurfaces or using Attosecond to generate beams with self-torque in other spectral regimes different from the extreme ultraviolet. Okay, still remember that we are still trying to solve this problem, to solve how to generate different harmonic orders, all of them with the same topological charge, so we can obtain an Attosecond vortex pulse. So again, if we look carefully in this scheme over here, we can see that all the harmonics, actually, they share similar topological charges. Yeah, if we look, for example, the topological charge 30 or 29 is shared, is there, is in each of them. So what we have to do is to pick the same topological charge at the different harmonics. How can we do this? Again, as we did it from the beginning, playing with the driving field, yeah, and playing with physical conserved quantities in the driving field. And what we are going to play now is with the linear momentum. And with the linear momentum, what we can do, for example, is to drive harmonic generation non-collinearly, okay, in this configuration, in which we have two vortex pulses with opposite topological charge, L equal 1 and L equal -1, and opposite spin angular momentum, 1 and -1. Okay? This is the intensity profile at the target, at the Garcia, and actually this is the tilt angle that we have at the target. And in this case, again, we can understand this scheme in harmonic generation using the photon picture. If we use the photon picture, now there is a difference against the other cases. Now photons on top of orbital angular momentum, they have spin angular momentum, and also they have linear momentum. They have direction over here. So for example, to generate the fifth harmonic, for simplicity, What we can do to generate the fifth harmonic is, for example, use 3 photons from this field and 2 photons from this field, okay? And 3 photons plus 2 photons, we have now to take into account the conservation of both linear spin and orbital angular momentum. And as a result, we have an harmonic that is emitted in this direction. The spin, if we sum spins, is -1, and the orbital angular momentum, if we sum orbital angular momentum, topological charges over there, is 1. Okay? Okay, this is one possibility, but we can pick also 3 photons from this one and 2 photons from this other one. And if we do that, as you may understand, what we end up is with the same harmonic order, the fifth harmonic order, emitted in this direction, this time with the spin 1 and with topological charge L equal 1. And in difference, on opposite to the previous cases, the collinear case in which we have many, many channels, here there are no more possibilities because of spin angular momentum conservation. Okay, if we take more photons than 1 from each driver compared to the other, the spin will be different from 1 or -1. So this is not allowed through spin angular momentum conservation, and we have only these 2 possibilities. What happens when we consider the rest of harmonics? What happens is at the end, we will have all the harmonics emitted in 2 main different directions, all of them with the same angular momentum, orbital angular momentum, and spin angular momentum. Okay, so in this scheme, we are left basically with 2 beam harmonics. Each harmonic has a slightly different direction, okay, because of linear momentum conservation. But what is important for us is that all harmonics are emitted with the same orbital angular momentum at the same spin angular momentum. And this, here you can see the results from theory and experiment that these harmonics are overimposed in the far field. This is superposition of harmonics from 15 to 23rd. And here you can see the theoretical results of the 2 harmonic beams, right circular, left circular, the amplitude, the phase, and the topological charge. And this is the result of the experiment performed in the group of Chip Darby in Colorado School of Mines, work performed mainly by David Schmidt. And here, although we don't have the full resolution, spatial resolution to see the singularities, we do have the confirmation that we have that scheme. And in our simulations, we extracted that actually, in this case, these beams, these harmonic beams, are emitted as Attosecond vortex pulse streams. Okay, so we were able finally to generate vortices that are emitted as Attosecond pulses. Okay, so these are some of the examples of the many fancy different works that we have done to generate a structured light in the extreme ultraviolet with harmonics. Now they are starting to do applications. When you think about application of all these fancy structured light beams in the extreme ultraviolet, you may think of applications that make use of the spatial domain. Yeah, because of the orbital angular momentum and so on. So, for example, there is an application using harmonic vortices for imaging in the group of Henry Compton and Margaret Moonlane that you can see over here. But all this work is not only to generate fancy beams. Yeah, we can use angular momentum also to control the standard properties of harmonics and Attosecond pulses. Let me put you an example. So we know in harmonic generation that typically we generate odd order harmonics, and the line spacing in the cone is of 2 omega because only odd harmonics are generated. And this is a result of the nature of harmonic generation, the nature of the 3-step process that takes place twice per cycle. So we have 2 events per cycle, okay, translated in the spectral domain. This is a comb of harmonics that are separated by 2 omega. But why, if we want to generate an harmonic comb where the harmonics are separated by 10 omega, for example? So this would require that we have 10 events per cycle. And you may think, okay, this is not possible in harmonic generation, yeah, because we have in one cycle, we have only ionization of the 2, let's say, maxima or minima, and to drive the harmonic generation process. However, with the structured light, we can make this happen. Yeah. we can, for example, design a driving field like this one, which is composed of 3 lobes whose phase is slightly different. Okay, if we drive harmonics with these 5 lobes, for example, we will generate 5 lobes of harmonics. Yeah, in each of the lobes we have a standard harmonic generation, but if we look at the interference on axis, as each of the lobes generates harmonics with different phase, they are properly delayed in time, and the proper addition of them results in 10 events per cycle. So the on-axis emission that we have in the far field, it is composed actually as a comb of harmonics separated by 10 omega. How can we generate this driving field? As simple as composing 2 beams with L equal 2 and L equal -3. Yeah, well, that's simple. I'm saying this as theoretician, experimental, this is complicated. Fortunately, our colleagues at the University of Colorado, and this was work experimentally done by Nathan Brooks and Quinn in Guyana, theoretically by Laura Rego, they were able to confirm our predictions, and in an experiment made in argon, if we look on axis, we see that some harmonics are gone, and this is precisely through this selection allowed by the design of these beams through orbital angular momentum. Okay, this is one example of how can we control the properties of the harmonics through structured light. Another example that is ongoing work we are developing with Melvin Redon and Kurt Arnon in Lund University with our student Rodrigo Martin Hernandez is using, for example, these hollow Gaussian beams to control the divergence of the harmonics. Typically with standard Gaussian beams, the divergence of the harmonics increases with the harmonic order. And this is not good for refocusing after the harmonics. Okay, this is really bad for proper refocusing of the harmonics. So what we were able to do is, okay, by driving harmonics with this ring profile with flat phase, which is called a hollow Gaussian beam, we demonstrated that the divergence of the harmonics decreases with the harmonic order. Okay, and this is a very nice result that is now in preparation. Okay, so this is more or less the roadmap we've done, and let me just finish by this third part of our most recent work is in working with spatiotemporal optical pulses, spatiotemporal optical vortices, what is called STOVs. Yeah, so this is a work we've done in combination with our theoretical colleague Miguel Ángel Porras and the group of Henry Captain and Margaret Murnane, and in particular with Guan and Chen Ting. So let me just briefly introduce what is a spatiotemporal optical vortice STOV. Typically, the vortices I told you before are vortices that they have the singularity along the propagation direction. Yeah, they are defined in the XY plane, in the transverse plane. If we rotate these vortices, yeah, and we can generate a vortice, which is called spatiotemporal vortice, that the singularity lies along this axis, and now the phase distribution is along one spatial axis and the temporal axis. Yeah. So here you can see the difference between a Gaussian beam and a spatiotemporal vortex. Yeah, this is space, this is time, and here you can see how is the singularity. These vortices, these spatial vortices, STOVs, they have been generated already in quite many works with different applications, but they have, for us, they have quite a complication. They are quite special because they are non-propagating eigenmodes. In difference with the optical vortices that can be very well described with Laguerre Gaussian functions, these guys are non-propagating eigenmodes. This means that if we have, for example, a STOV at a lens that is focused, what we have at the focus is not anymore a STOV. Yeah, it has this tilted profile, tilted intensity profile, that if it propagates again to the far field, it recovers this STOV profile. There is a very nice conjugation between temporal and spectral domain, because at the focus where we have this tilted intensity profile, yeah, we have actually a spatiospectral STOV that you can see over here. And actually, we can have two different configurations, a configuration in which we have a STOV at the lens that is focused, and we have a spatiospectral STOV at the focus, or a spatiospectral STOV at the lens that when it's focused, we have a STOV. We will call this elliptical STOV, this kind of a scheme, and this other scheme as elliptical spatiospectral optical vortice. So These spatiotemporal optical vortices have been generated, and a lot of work in the group of Howard-Mitchell have demonstrated the generation of these particular spatiotemporal vortices. But again, here the challenge for us is, okay, if we would like to bring them to the Attosecond extreme ultraviolet regime, we have same limitations with the devices that are typically used. So once more, we can use nonlinear optics to try to bring these stuffs into the higher frequency regime. And this was first done in second harmonic generation in two different works by the group of Henry Captain and Margaret Murnane and the group by Howard Milsberg. But what you can imagine what we're going to do now is to use harmonic generation and to see how in harmonic generation these stuffs are converted into the extreme ultraviolet. And actually, I have to tell that this was already proposed theoretically by the group of Jung-Kwan Liu back in 2021. Actually, there is some relationship between to see that in harmonic generation, there's been previous works in using spatiotemporal properties, and maybe you can recall the Attosecond lighthouse effect, which actually is coupling spatiotemporal properties using transverse spatial chirp, or using angular spatial chirp, we can also generate spatial chirp harmonics. So this other work of Stops is another work of spatiotemporal coupling in harmonic generation, but having that phase singularity in the spatiotemporal profile. So this is the work that we propose to having a stove at the gas jet. And if we have a stove at the gas jet, we have harmonics that are generated at the stoves that are propagated into the far field of spatiospectral optical vortices. And when refocused, we can have spatiotemporal optical vortices. So we performed the simulations at the University of Salamanca, and this is the far field emission that we got, the harmonics that are, this is the spectral profile, that harmonics that are actually generated as spatiospectral optical vortices. Very well, in the temporal domain, this is the structure, this tilted structure, but if we refocus these harmonics, what we obtain actually is that the refocused harmonics, as we expected, we can have stoves. And what we observed, as predicted in the work by Jung-Kwan Liu, is that the topological charge of these stoves follows the conservation of orbital angular momentum preserved at this scaling of the topological charge. So our colleagues at the University of Colorado, they performed the experiment, and it was quite a very complex experiment, and also very complex comparison between the theoretical and experiment, because this is, for example, what they got. They got harmonics that are emitted at two stripes. And what we were expected from the previous result I told you, we should be expecting this full ring as a spatiospectral optical vortices. And you can see that the comparison was not perfect, was quite difficult for us to have. So this was like 1 or 2 years of work trying to understand this. And what we end up understanding is that actually, if you change the driving field from a perfect stuff, from a non-perfect stuff, as it was happening in the experiment, you can see how the harmonics, they go in the spatiospectral domain from a full ring profile to two stripes, preserving the phase profile with this stuff. So we now, keeping this in mind, we perform the comparison between our numerical simulations and experiments, and actually we did it for different positions of the gas jet versus the focal position, and you can see that the comparison, taking into account the inhomogeneity of the driving field, was really good. So we were able to confirm the generation of extreme ultraviolet spatiotemporal optical vortices, and we were really happy to have this work that has been recently accepted in Nature Photonics. Okay, so I could be able to be talking to you more about the structured light. There are more structure fun, like for example, the generation of vector beams, this kind of radially polarized or linearly polarized beams. Using also solids in harmonic generation, like graphene, where we, for example, develop this work of topological harmonic spectroscopy, or more fun that we've also been developing using these azimutally polarized beams to generate ultrafast magnetic fields that are isolated from the electric field. So these are more works that if you would like to have more fun looking into structured light, I would recommend you. So I will now conclude that basically I would just like to tell you that the structured light beams at the Attosecond timescale can be generated. opening really exciting perspectives to study ultrafast laser matter interaction. And I would like also to conclude giving you a gift for you, if you would like to play with this kind of beams that you can see over here. We have developed an open access and open platform that we've called ATG Studio that you can download freely from this link over here. Here you have the QR code, and you can play with it. You can perform simulations of harmonic generation with these vortices and playing with many different features of harmonic generation, looking at the time frequency analysis, phase profiles, so on and so on. We are developing it. We are very open to any suggestions you might have using it, and I would really recommend you if you would like to play with these simulations. Let me just thank our collaborators. I told them during the talk, the group of Henry Captain Margaret Bournain, the group of Chip Duffy, Miguel Ángel Porras at Madrid, the group of Sophie Casamías, and many other collaborators and many other works with them. Let me just briefly present our group in the University of Salamanca. We are a very varied group with different research lines related to ultrafast optics. The research line related to the theory of harmonic generation and structured attosecond pulses. This is the people in work, including our former PhD students. And just let me thank you for your attention, and I'm really open to many questions you might have.
Thank you. It was a really nice talk and very impressive work on structured light. I'm sure we learned a lot. So are there questions, comments? Please write in the Q&A tab or raise your hand. We have one from anonymous attendee. How can structured light be used to study electron dynamics?
Oh, very interesting thing. How to study electrodynamics. Okay, so for example, one of the works that we've been developing in this topological harmonic spectroscopy that was over here is if you derive harmonics with topological properties, you can identify from the topological properties of the harmonics that are generated, you can identify cycle dynamics that are happening. So for example, we know in harmonic generation in solids that there are contributions from interband or intraband contributions in harmonic generation. What we observe is that the properties, the topological properties of harmonics are different depending on these different contributions. Yeah. So this is one example. I think, for example, this is really interesting for anisotropic materials. Yeah, like these solids, these crystals. But if you look into heterostructures or to some solids with imperfections, I think that through the topology of the harmonics that are being generated, you will be able to learn more things about the electronic dynamics that are happening over there.
Okay, are there further questions? Just to say that today we are trying our chat feature on YouTube, but only for subscribers. So if you are a subscriber of this page and are watching on YouTube right now, I know some people are, just post a question in the chat and we are going to answer live. Otherwise, subscribe and maybe next time. But we are also here on Zoom. So are there any more questions? I see only one so far, but I know this is a really interesting topic. So how do you observe, another anonymous person, how do you observe the interactions such as ionization instead of high harmonic generation? Let's say if you would do this thing for ionization, I don't know if I'm being correct. How do you access the recording? I joined late. Okay. You have to wait until it's published on YouTube. But anyway.
Maybe, yeah, related to ionization, I know that there is people looking not only into the harmonics, and we are looking at the photoelectron spectrum, especially resolved photoelectron spectrum. It's also very interesting. Okay, and there are many works, for example, using circularly polarized harmonics and to see how are the photoelectrons, the distribution of photoelectron distribution. And I'm sure Carla, for example, you will be able also to add in this part over here. Yeah.
Yes, I mean, in principle, these whole processes, they are enabled and powered by the field. So if you want to do whatever he has done here with harmonics, which is a huge amount, in principle, you can do with photoelectrons. And there's a huge field, which is the field of photoelectron holography, where you find ways to imprint the characteristics of the field in the photoelectron spectra, and you can manipulate them so that you can get similar things. In fact, there is some work, not only by our group, but by other people as well, where people have been looking at vortices, how you create photoelectron vortices and how you imprint orbital angular momentum of light in photoelectrons and vice versa. So in this case, light from photoelectrons, if you're interested in ionization. So really, it is pretty much the same basic principles, and there are a few groups doing this. We did some work on this. People in Poland did some work on that. I mean, there are many. Just Google.
It is more by Tony Storas and their colleagues. They were also doing this, yeah.
Exactly. So you have a lot of work on the US. So it's pretty much a similar principle, if you wish. And I'm sorry to hear you joined late, just coming back, but we release this on Monday or early next week, edited. We run this through the speaker, and then if the speaker gives us okay, you can access it. But you never know what the speaker wants us to remove. They are the boss. We remove whatever they want. So if you want to see and listen to the talk fully, it's better to catch it live. Okay? But you'll find it, it's released on Monday, Tuesday on YouTube. How can you detect anonymous? How can you detect after generation if the beam has either +1 or -1?
Good. +1 or -1. So there are different, yeah. There are different, let me just check 1 second, because I think I have a slide that can help me to answer this. There are different, yes, I have it. There are different experimental techniques to characterize the topological chart of harmonics. So this is through interferometry, okay, in the group of Paul Corkum, and they develop, and you can see, for example, here in this case, characterizing the 11th harmonic, yeah, with different and opposite topological charts, as you can see over here. So I think the direction of the fringes in the interferometry can tell you about this. The group of Sophie Casamias, for example, they have developed using wavefront sensors. So wavefront sensors, depending on the direction of the phase, you can also be able to characterize them. And in the group of Thierry Gouchon, for example, they were able to characterize the topological charts through rabbit measurements. I'm not sure in this one how would be the result for opposite topological charts, but I think it could be worked out. I hope this answers the question.
Yeah, I hope so. Is that okay for you? Yes, okay, difficult to say, but I hope so. Would anybody else like to ask anything? No open questions. So on YouTube also, we didn't have any questions. We're trying this time, but you have to subscribe, you know. So one question, what would be the application? Because I have seen that you have been putting a lot of effort to try to get all the harmonics with the same orbital angular momentum. What would be the main application for that?
So I think in that case, we can talk about, let me go to the, I can put the slide for that. In such a case, I think it's this one. Yeah. In such a case, I would say that many of the applications we have with Attosecond pulses, for example, transient absorption, spectroscopy, and so on, we can now see what happens when we have an attosecond pulse with orbital angular momentum that interacts with the material at that time scale. Yeah, I think at that time, until now, we haven't had a pulse that exhibits topological charge at the attosecond time scale. This is the first time we have these pulses. So in my mind, innocent mind, I would say, okay, all the applications of attosecond pulses, especially transient absorption or spectroscopy and so on, now we have the interaction at these timescales of a beam with OAM. How is this affecting, for example, excitations and different, in different neurons, molecules, so on? We can now think that we have the interaction at the attosecond scale with orbital angular momentum. I don't know exactly which will be the result, but now I have this tool with this potential tool to see that the interactions that we have at the attosecond time scale, we can have them now with this property of OAM.
Mhm.
So I'm really eager to hear potential applications too. I'm more into the light science, but I know that well, I think it opens something that could be studied at least.
No, definitely, because if you think even people who have done stuff in the other direction, like when they use optical tweezers and these kinds of things, they apply these a lot in biology and in other fields,
Yeah.
right?
Well,
So
optical tweezer at the attosecond time scale, that would be cool. I mean, I don't know, of course, that what kind of time scale at which optical tweezers are used nowadays is, I mean, I think they're using them at longer time scales. Yeah, what I know, but yeah,
yeah, I'm just speculating while I'm waiting for
yeah,
questions, you know.
yeah, yeah.
Uh, anyway, I think we are good with questions, right? Would anybody else like to raise your hand and ask something? I don't see anybody. But definitely there is a lot of possibility for structured light. And we are pleased. We have one. Anonymous. What is the interest of reaching an harmonic with topological charge of high L?
Good. Good question. So the interest that drove me to go to high L is the following. The dream experiment for me would be to make an OAM pulse to interact with a single atom, for example, or a single molecule. But we have a problem of scales there, yeah, because is the atom or the molecule gonna feel the phase profile? Yeah, the beam is too big compared to the size of the atom or the molecule. But at the end, how big is compared to that is how quick is the variation of the phase uh, compared to the atom or the molecule. So when going to high topological charges, I think that we are closer to be able to perform an interaction in which the atom or the molecule or whatever it is can feel the orbital angular momentum of the light beam. This is what drove me. I think we are still a little bit far from that, but this is at least the direction I was thinking when doing this kind of works. Then, I mean, for other applications, not that they are a second time scale, high topological charges at the infrared, they're used for communications a lot. Okay, there is a lot of work going on in, including encoding information in the orbital angular momentum of light. Very nice work in that. And of course, as many topological charges there can be, but this is, of course, out of the scope of Attosecond.
Very good. We have a lot of questions. Another one. And what is the highest that you were able to reach, just out of curiosity?
The highest L, or sorry?
Yes, I think that's what they mean.
Yeah, the highest topological charge is 100. Let me go back to the slide I used. Is this one? This is in this work that is over here. The experiment was performed in the loop of Sophie Casadias by Alok Pandey. And this is the waveform measure. Of course, it was really challenging experimental, and I have to give them a lot of credit to the experiment because you have to resolve 102 pi shifts into your wavefront sensor in the UV. So this is what they did. Of course, there is some uncertainty because it was really challenging to do this, but this was proving that would be able to generate harmonics up to 100 using a driving theme of L equal 4 in the 25th harmonic. If we use higher driving themes with higher topological charge, probably, of course, through this scaling law, we will be able to generate higher topological charge, but of course, it will be more challenging to measure them. Yeah.
So you will have the opportunity. We're going to stop the live streaming right now. So for those who are watching on YouTube, and there are quite a few of you today, thank you for joining. Thank you for supporting us. If you want to ask questions on YouTube, don't forget to subscribe, and see you everybody in 2 weeks. Stay safe and take care.